then we can smoothly move into John tools. Please go ahead for it, John.
Okay, so thanks so much, David. The fantastic presentation. It's also interesting to have an agency perspective and an industry perspective of these missions, and also one of the things that I think David mentioned was that in the ITT, it is a challenge phase, and it was very welcoming to have the possibility to challenge the way things have been done before, and certainly we do try and do things differently, aiming to try and achieve the first requirement, which is to land on the moon in 2026. But from this first slide, it's not easy to execute this process, and it's going to be very, very difficult to execute it on the surface of the moon. So for anyone not familiar with the Metalysis process, it's a process that I think was invented in the 80s, 70s in Cambridge. It used to be called the Cambridge FFC process, and Metalysis bought the rights to the process. And Metalysis are a metallurgy company in Sheffield who have the process, and they find that they can extract very small quantities of metal, which they can then use in quite exotic alloys. So the basic process is, number one, there's a metal oxide powder. You see there, it's preformed into a pellet, and I'll come on to that later before it goes into the process. It goes into the process in molten salt, and they pass a current through, and what comes out is at that stage, and top right you can see the chemistry. On Earth they use a graphite anode, and they actually produce carbon dioxide. We have a slightly different anode material to produce oxygen. So that's the first divergence really from the terrestrial process. Then a metal sponge comes out, it gets crushed and milled, and then one of the terms you may hear is salt drag out. That on Earth you can have this metal sponge and you can take it away from the molten salt, and it's no big deal to wash it with water to remove the salt to leave a dried metal powder. That's something that will be more difficult on the surface of the moon, but what we are doing is just the demonstration mission, just to demonstrate that the chemistry can operate on the surface of the moon. The technology scope quickly, and these are all the metals that Metalysis do extract from small quantities of raw feedstock. And again, there was a little bit of overlap on the presentation today between mine and David, so I'm taking the opportunity to present Metalysis slides from Space Resources Week a couple of weeks back to highlight the process. They start off with their generation 1 processor, and then they scale up to generation 2, an order of magnitude bigger, generation 3 and generation 4. So that gives us the model for the pilot plants and scaling up the pilot plants. And we hope to, after our demonstration mission, to scale up the pilot accordingly. I'll quickly go on to this one. Where Metalysis are giving us valuable insight is how to optimize the process. As I said, the process was originally designed for the metals market, metals industry, metal production, but they've changed the process to produce oxygen, and they're looking at how they can optimize the oxygen from the demonstration mission. And on the demonstration mission, one of the key targets we have been given is the number of the amount of oxygen that we can produce for the amount of mass. And as I say, we're looking at ways of maximizing the amount of mass. And again, you see that ESA with their pilot plant in Estec, I think it is, with Beth and Alexandra, are also doing research in this area. And this is key. The chemistry is key to what we're doing. So if I quickly go back to the slides where we had the duplication, there were, again, in the challenge phase, things were done differently. We were competing against 3 other teams, and we were very, very lucky and happy to be selected. So that's Tyler's Linear Space, AVS, Metalysis, and Open University in the UK, and Redwire in the in Luxembourg. And I say we were given the target of accommodating the payload onto either a commercial lander or an institutional lander. And so in order to demonstrate our payload can be mounted on a commercial lander, we had to reduce the mass as low as possible. So in this picture, you see one of our old designs. I say we're commercially confidential at the moment, and so unfortunately can't present the details of what's inside the boxes, and giving you a design that is about 6 months out of date. We've gone through quite a stringent design review activity to remove about 10 kilos of mass from our payload concepts. So this white box on top is put onto a notional nominal lander, but we think that we can achieve the build of a demonstration mission to demonstrate the chemistry on the surface of the moon for under 79 kilos. So 9.5 kilos of that is the robot arm and the regolith acquisition. As David mentioned, then there's the handling the regolith after we've removed it from the surface of the moon, and the chemistry on board the lander in the reaction plant. We don't have enough mass to store the oxygen generated, but we do analyze the products generated from the reactor to demonstrate that we are producing oxygen. It's not that we've carried any oxygen in any materials that we've taken up to the surface of the moon, and we do need to demonstrate it. I say the challenge is the not just the mass, but then the energy and the power provided to us to heat up the salt, to melt it, and to also make sure that we can demonstrate all aspects of the process. I say the concept is to demonstrate the mission goals. Follow-on missions may start to determine pilot plants, as David said. So there could be a unit to produce oxygen that can be moved around the moon. Tight mass and power requirements, very, very tight, and we're currently reworking the spreadsheet now to see what the timeline is for the mass and power. There is high yield of extraction of oxygen, and we're looking to optimize it. But and again, if anyone does have a key technology or key research that they would like to make us aware, we're finding that this has not been done by anyone before, of course, and we're finding that there are areas of technology that would apply to what we're doing where we wouldn't expect to see them. So, for example, in terms of the processing of the material before it goes into the reactor, where we try and process it into that pellet. I won't say how we're processing it at the moment, but that processing of the pellet before it goes into the molten salt, I found out just a few weeks ago that the ceramics industry have done a lot of research for the last century or so how to put similar feedstock into a kiln for their ceramics process. So say it's all very new. We're looking for expertise, equipment, and facilities. The difficult part is the part that David mentioned in terms of the technology demonstration, the Technos to TRL5. We have lots of key areas of uncertainties and unknowns to deal with, from how the regolith would behave to a scooping action, to the chemistry within the reaction plant. But that period is crucial, and we're looking to gather as much information as we can about research relevant to this area and facilities where we can do the testing. So, for example, dusty vacuum chambers. So, if I may finish there, and if there are any questions for me or David.
Yes, please. Thanks, John and David. We are in fact ahead of time, so please let's go on with a question. There is a question from Philip Rice on the chat box. Question for John: will the demonstration model also include demonstration of the purification and storage of gas products on board?
No, it won't. No, it won't. But there are technologies, and that would be the next phase to extend outwards for the purification and the storage. Again, we have ideas on how to do the storage, and that could be again a later development. But the purification and storage is key. But we're confident that if we had the mass, we'd be able to put it into the design concept. When David gave us the requirements, he gave us baseline mission requirements, and then he also had stretch requirements, extended mission requirements, and we actually developed a scheme for the purification and storage in the extended mission. But we didn't have the mass to fully take it on board. But that's one of the areas where the technology uncertainty is quite low. We think that the technology readiness of the oxygen purification storage is not so difficult as the Metalysis FFC process, or the handling of the regolith, which is just, everyone knows in this symposium, it is something that we just, there's nothing like it on Earth.
Okay, thanks. Mahesh, go ahead, please.
Yeah, it's a question probably for both John and David. When David, you alluded to hydrogen reduction on the moon, as I understood, the idea has always been that if you could demonstrate by taking some hydrogen to the moon that this works, later on, there is plenty of hydrogen derived from solar, wind, and other sources, for example, on the moon, that could then, facilitate a more scalable operation. For the FFC process, what are the thoughts? Because you have to take the salt with you, a lot of chloride salt. So once you demonstrate it, what are the thoughts that how in future, how could that be sustained based on the local resources on the moon?
Do you want me to take it, John?
Yes, please.
Well, the salt we always consider it's not a consumable. So generally speaking, no salt is lost in the reaction. I mean, inevitably there will be some losses. There always is. No system is perfect. So one of the technologies we have to master, which we feel we can better do on ground, is to master salt retention in the system. I mean, so this is identified by ESA as one of the key parts of the FFC. I mean, we have to retain most of the salt and do multiple runs of oxygen production on that same batch of salt, so the mass balance closes, so to speak. The hydrogen reduction. This is part of a wider system trade-off. There is an advantage that it's very simple, but the disadvantage is extremely low yield. It's an order of magnitude worse in principle on the stoichiometry against something like FFC. or even the molten oxide electrolysis processes, which have different disadvantages compared to hydrogen reduction. So it's, I mean, with hydrogen reduction, you need to dig more of the moon up, basically, to acquire your resources. With FFC, you will get, if you leave your system to run long enough and you have enough power, you in principle can acquire all the metals and oxygen and make this conversion. And the salt is reduced. Naturally, everything needs maintained, of course. But on a benefit analysis, the FFC does give you a bit more return on that regard.
So I see that currently the idea is that whatever salt is required will be carried from the earth. That's
yes.
what it is. Yeah.
Yes.
Thanks.
Now we want to we want to have no consumables, and FFC in principle in a perfect world would create a system where we have no consumables. But hydrogen reduction, there will always be consumables unless you recovered your hydrogen and you just stuck with the oxygen.
Thanks. There is maybe time for a last question. Francisco Javier Guerrero Gonzalez, question for John again. What are the benefits of reducing compressed regolith pellets instead of directly the powder as it was done in Lomax experiments?
The benefits are that you have a more controlled reaction. So in terms of how the process works, you're looking to the process will liberate the oxygen from, I think, the first 100 microns of the surface area. So you're looking to present a large surface area to the salt, so the salt can permeate through it, and we have requirements for porosity. But you don't want to end up with a sludge in the bottom of the tank, as it were. So you do want to take out the sponge, the metal sponge that I showed you in the metalysis slide earlier on. So it's an advantage for handling. And one thing I didn't mention, another advantage of the FFC process, it doesn't mind if it's reducing aluminium oxide, iron oxide, or titanium oxide. So it can have a wide range of minerals that it can process. So we are able to land on a lander, and then pretty much if there is a regolith powder available within the reach of the arm, we will be able to process it to get oxygen. The trick there is then to make sure that we characterize it, everything that goes into the reaction, and characterize everything that comes out again.
Thanks. I think we are done for this first part of the morning. Thanks very much, and please, Nicole, go ahead.